In addition to seeing Jill seeing Jack falling into the black hole, she's also struck by the sights around her. They didn't just plan their stunt in an isolated location. They planned it in an area that abounded with background stars. This gave both of them some amazing views of the background stars that were quite unexpected. Because general relativity states that spacetime is curved, the most important element of that statement is that straight lines through curved space appear to a distant observer to have been bent, warped, or shifted. From the observer's perspective, where you perceive that you are looking in a straight line over there, your intuition tells you that straight lines emanate from your eyes, from the source to the destination. However, this perception is incorrect or at least highly deceptive. The actual path of light from its emission to its reception is by definition in a straight line. Light only takes straight lines in its travels. Very technically, light parallel transports along a null geodesic and therefore takes the shortest possible path from the source to the destination. This parallel transport assures that the arrow pointing in the direction of light's travel does not change direction from one step to the next. Without a change in the orientation of light's direction of propagation, it is moving in a straight line. But then, why does everyone say that light's path is deflected, bent, or warped? This is because we have a cultural bias of being a distant observer, that we can see the background stars and with practically no curvature between us and them. The marauding black hole's gravitational well, caused by the curvature produced by the Schwarzschild metric, shows us an image of a distant object beyond the black hole, which is not representative of its true spatial position. Thus, the curvature of spacetime distorts our view of a distant object, creating images that change the apparent position of the background object to a new location. In this little cartoon, the object in the middle is the blue ball. Light emitted from this blue ball travels along the arrowed lines, always going in a straight line until they get to the observer's eye. Now, this path looks bent, but the spacetime is curved. Therefore, the straight lines in the curved space around the red thingy, which for us could be a black hole. Now, as observers, we look in a particular direction, say the top one. We see an image of the object in the direction that is above the red dot. The light rays are also bent to form a second image below the red dot. And it's really important to note that we do not see the blue ball in the middle. The light from the blue ball in the middle is sent on some other apparently curvy-wurvy straight path away from our observational location. We are then left only to see the two images above and below the red ball. It is in this sense that the trajectory of light's paths is changed from the straight lines of flat spacetime to the straight lines of curved spacetime. And this isn't just semantics or a trick or an illusion. Parallel transport in curved spacetime leads to fundamentally different results than in flat spacetime. The solid bent arrows are the true straight lines in curved space. They are not bent or deflected. The light is merely following the shortest path that parallel transports the tangent vector in the direction the light rays are pointed. As an important example that doesn't directly involve a black hole, but does involve curved spacetime, we reach back to April of 1990. 5 months after the launch of the Hubble Space Telescope, it captured 4 images of the same quasar in a gravitational lens, G2237 plus 0305. Called an Einstein cross, this image reveals a distant quasar gravitationally lensed 4 times by a relatively nearby galaxy. And as time went on, Hubble Space Telescope has observed a large number of these optical gravitational lenses. In 2002, astronauts on the Space Shuttle upgraded Hubble's imaging with the advanced camera for surveys. It had 5 times the previous sensitivity and observed some spectacular images of galaxy clusters gravitationally lensing some of the most distant objects we've ever seen. And one of them is this really fascinating and fortuitous observation of a background supernova being turned into an Einstein cross. The foreground galaxy cluster is about 5 billion light years away, and the distant supernova is about 9.3 billion light years away. The galaxy doing the lensing is the reddish blob, but the embedded distant galaxy is the bluish smear around it. The bluish smear is itself a strongly lensed background galaxy distorted by the path the light took on its way to our observational standpoint. On the right is the molten ring galaxy observed in 2021. This strongly distorted appearance is due again to the path the light traveled and not the galaxy's actual shape. The squishy appearance is also highly magnified. This magnification of about 20 times means that we see the faraway galaxy as larger, brighter, and distorted. Ophthalmologists and optometrists the world over would recognize such things as astigmatisms of the eye. But here, these astigmatisms aren't caused by a fluid or solid with some different refractive index than their surroundings, but rather due only to the shape of spacetime itself. With respect to our black hole simulation from before, we see an Einstein ring. Here, the ring is formed from the background light of the Milky Way being directed toward us, which would have gone in a different direction had the black hole not been in that position. The black hole changes the shape of spacetime and thus alters from flat spacetime the path of the light. The symmetry in the ring is due to the extremely symmetric spacetime metric around a non-rotating black hole as envisioned by Carl Schwarzschild. Next, we see Dr. Hamilton's simulation of how Earth would appear to behave if it were orbiting a black hole with a mass of 2,000 times that of the Sun and at a distance of only 3 times the Schwarzschild radius. And one could imagine this is an extreme and absurd example, but it serves to show the important effects of curved spacetime. 3 Schwarzschild radii is the minimum stable circular orbit, and we are observing this event from not very far away at a distance of only 5 Schwarzschild radii. First, we see the obvious gravitational lensing, which makes it look like the Earth is being squished and squished. While the tidal forces would be huge and destructive to the Earth, let's assume an indestructible Earth just to keep things going. Then the effect we're seeing is the trajectory of light being reflected off the Earth from some bright ambient source. We can then actually see multiple images of the Earth as it orbits the black hole. Next, as Earth moves away from us on the right-hand side of the orbit, we observe a redshift. The relativistic Doppler effect is coming into play here, principally caused by time dilation for light arising out of the gravitational well. The time dilation also makes us measure time on Earth to run more slowly as it moves away from us on the right-hand side. The opposite blue shift and time contraction would occur on the approaching side. If this were really happening, the Earth would be orbiting the black hole at about 80 times a second, and that would be pretty bad, and we've slowed this down a lot. We've also slowed down what would be the tidal shearing between both sides of the Earth that would rip it to shreds. For one of the most realistic simulations of the conditions around a black hole, we can watch Christopher Nolan's movie Interstellar. He worked with the famous relativity researcher Kip Thorne to produce very realistic light ray paths. The odd ring and upward flow are due to the way light travels in strongly curved spacetime only, and don't reflect the physical shape of the accretion disk around Gargantua. It does lead to some artistic embellishments. The actual shape of this halo would be more squared off, as well as dimmed and reddened on the receding side and strongly brightened and bluer on the approaching side, just like the Earth thing we saw a moment ago. Nolan said that adding these bits of realism made the environment harder to understand visually, and Thorne, a good friend of his, understood and agreed. And besides, it's a film, not an explicit scientific treatise.